So in this video lecture we'll be solving the T-beam and we'll be seeing numerical type 2, that is the design problem. In my previous video lectures I have taught you numerical type 1, in which we found the moment of resistance of a T-beam. If you have not watched that video, kindly watch that first. So here we have got a T-beam, and the procedure for designing is, it again goes through the three cases that I had told you in my previous lectures. Case 1 being that your actual neutral axis is less than or equal to df. This is an assumption and this is a case 1. So what we assume in this is that, let us say xu is equal to df. See, xu is less than or equal to df, so the extreme case of this condition will be when xu is equal to df, right? So assuming this case, we will find the moment of resistance first, that xu is equal to df. So this is equal to df, okay? And whatever moment of resistance will come using this stress diagram, it will be MUF. MUF is 0.36 FCK BF into df, because this is the total depth, into d minus 0.42 df. So what this MUF is actually is, it is the moment of resistance due to flange, because when we are considering xu is equal to df, we are assuming that this entire flange is contributing to the moment of resistance, correct? Because your xu is equal to df, and therefore this we denote it as MUF, which means the moment of resistance due to entire flange. Now in design type of problems, one thing that is given to you is loading. Loading is given to you. From loading, what you can find is ultimate moment, what we call it as MU. MU can be found out. So basically MU is given to you, okay, in this type of problems. We have MU, we have MUF. So if MU is the actual moment coming due to load, consider possibility of following two stress diagrams. So these two stress diagrams are possible if we know MU, and here see what I have written. If MU is less than MUF, then XU is less than DF. How did I come to this conclusion? So see, MU, the formula for MU, generally what we write is 0.36 FCK BXU into D minus 0.42 XU. What I can see from this formula is MU is directly proportional to XU, correct? MUF is directly proportional to df, right? So if mu is less than muf, does not that mean that xu is less than df, correct? So from this case, when we know mu and when we know muf, if we compare both the moment values, we can say that whether this xu is less than df or not, and if it is less than df, then our case 1 is correct. So we have to proceed with this case 1. So if mu is less than df, then this stress diagram is correct. You can see here xu is less than df, right? So this stress diagram is correct, and then we can proceed with this stress diagram further to find the actual neutral axis depth, because from comparing mu and MUF, what I only came to know was whether if XU is less than DF or not, but I could not find the actual value of XU till now. So we need to find that actual value of XU, that is the actual neutral axis depth, and that is found by MU is equal to 0.36 FCK BF XU into D minus 0.42 XU. So I know MU, I know FCK, I would know the effective flange width, D I would know. The only unknown in this would be XU. So I can find the actual neutral axis depth, and after I find actual neutral axis depth, what I can do, I can find ASD. How? So 0.36 FCK BF XU is equal to 0.87 FI ASD, that is, we equated the compression force to tension force, and from this the only unknown that would remain is AST, and then I can find this steel. So in design problem, generally finding steel is more important, because how much reinforcement you need to put into your member, that is more important. Coming to the next case, that if XU is not less than DF, that is if XU is greater than DF, or how did I come to know that? It will be if MU is greater than MUF, then obviously XU will be greater than DF. So in that case, what to do? In that case, we come to case number 2, in which we know that our XU has exceeded our flange depth, and then we will check that whether 3/7 XU is greater than or equal to DF or not. Now we will check one of the limiting conditions of this, that is 3/7. We will assume that 3/7 XU is equal to DF. Okay, so we will assume such a case that your 3/7 XU, that is the, sorry, I think it's a little bit down, that is your depth till the stress is constant, that 3/7 XU, we are assuming it equal to DF. It is one of the limiting conditions of this case 2, right? And then we try to find the moment of resistance for this particular diagram. So the moment of resistance found using this stress diagram will be, it is 0.36 FCK BWXU. I hope you know how we have found this, how we came to these two formulas, because I have already explained this in my previous lectures. So it's 0.36 FCK BWXU into D minus 0.42 XU plus, due to the flange, this was due to the web, this moment of resistance is due to the flange. So it is 0.44 FCK BF minus BW into DF into D minus DF by 2. Now what is unknown in this, because we have to find this MUW. This MUW represents that when your neutral axis, I'm really sorry that this XU will not be till here, it will be till here, okay, till here, till this point is 3/7 XU, right? So this, what this MUW states that your neutral axis has gone into the web, and now we are finding the moment of resistance due to the web. But in this also it is asking the XU value, and you don't know the XU value, exact XU value you don't know, but you know one condition that we had assumed, that 3/7 XU is equal to DF. From this what I can say, that XU is equal to 7/3 of DF, and this I can substitute here because DF value I already know. So after I substitute XU as 7/3 DF, this is the equation that I get. This is the equation of MUW, that is moment of resistance in the web. I get this entire big equation, and after I solve it I will get the value of MUW. Again I have the value of MU with me, that is the ultimate moment coming due to the load. If I compare the value of MU with MUW, I will get again two possibilities I will get. First possibility would be that MU, if MU is greater than MUW, then 3/7 XU is greater than DF. Okay, if MU is greater than MUW, then 3/7 XU is greater than DF. If you ask how, then MU is directly proportional to XU and MUW is directly proportional to 7/3 of DF. So if I say that MU is greater than MUW, if MU is greater than MUW, does not that mean that XU is greater than 7/3 of DF? And then if I rearrange the term, what I'll get, 3/7 XU is greater than DF, correct? So from this case, when I compare the value of MU and MUW, I will understand that whether 3/7 XU is greater than DF or it is not greater than DF. Yeah, either values I can understand, but first in this case I am considering that MU is greater than MUW. I got, let's say, MU greater than MUW, and I got this 3 by 7 XU greater than DF. So this is how the stress diagram will now look, and therefore now we can calculate, let us assume that this case is true for us. So now we can calculate the actual neutral axis, because till now I have not got the actual value of XU. So I have to find the actual neutral axis depth XU. So mu is equal to 0.36 FCK BW XU into D minus 0.42 XU plus 0.44 FCK BF minus BW DF into D minus DF by 2. Fine. This is the case. So if I equate, I know mu basically, I know FCK, I know BW, XU is unknown, D is known, XU is again unknown, FCK is known, this is known, this is known. Everything is known except XU, so that can be found out. And then again, to find AST, what I can do, I can equate the compression force to tension force for this particular case, that is 3 by 7 XU greater than DF, and I can find the AST. So we found the steel for case 2. But now what will happen if mu is less than MUW? It means that 3 by 7 XU is less than DF. So that becomes our case 3, where 3 by 7 XU is less than DF, and our stress diagram will look something like this, where this is the 3 by 7 XU and it is less than DF. Okay. So if the case 1 and case 2 both come out to be wrong, then obviously case 3 is correct, and then you have to go ahead with it, because it is only the correct option. So in case 3 we have a parameter YF which is given in IS code, and YF comes out to be 0.15 XU plus 0.65 DF, and the moment of resistance equation for this is 0.36 FCK BW XU into D minus 0.42 XU. This is due to the web, plus 0.444 FCK BF minus BW into YF into D minus YF by 2. Now here what you will have to do is you will have to substitute the equation of YF, that is 0.15 XU plus 0.65 DF. This you will have to put in YF. So essentially in this equation the only unknown that will remain would be XU, correct? And then after finding XU you can find AST. So we would, after finding XU, you would know the actual value of YF also, so you can directly put the value of YF here, that is we are equating the compression force to tension force, and the only unknown that would remain is AST. So we again find AST for case 3. So yeah, so this is how we have to go ahead with the design numerical of a T-beam, and let us now solve a numerical. So what is given to us is a T-beam having effective flange width of 1000 mm. Again, effective flange width is given, so you need not find the effective flange width using any other formula. 1000 mm and depth of flange as 100 mm, width of web 250 mm and overall depth of 550 mm. So depth of flange, width of web and overall depth is given. The beam is supposed to resist 500 kilonewton meter ultimate moment. So instead of giving the load, they have directly given the ultimate moment. Use M25 Fe500. Let effective cover be 50 mm. So this is how the T-beam would look. 1000 mm of effective flange width, 100 mm depth, flange depth. 500 mm would be effective depth, because total depth is 550. So 550 minus 50 would be 500. 250 is the web width. So all these things are given, FCK, Fy, your ultimate moment, Mu, everything is given. So we should directly jump into solving this, and considering the case 1, that is to check that if XU is less than equal to DF. So one of the limiting values of this would be XU equals to DF. We have to assume this value first. So assume XU equals to DF and find moment of resistance of flange MUF. MUF is 0.36 FCK BF DF into D minus 0.42 DF. Again, these formulas we have already visited in the previous classes as well. So if you have not seen, you should always see the class in sequence, only then you will understand. So MUF is 0.36 into FCK 25,000 into 1000 into 100 into 500 minus 0.42 DF. MUF I get as 412.2 kilonewton meter, and immediately I have my MU value, which is 500 kilonewton. So I can say that this is less than MU. So if MUF is less than MU, what we can say that DF is less than XU, or basically XU is greater than DF. So case 1 is not correct, right? So since MUF is less than MU, hence XU is greater than DF, and this assumption or this case is wrong. So we have to move to the case 2 by knowing the fact that our XU has exceeded into the web, and then we need to check that whether 3/7 XU is greater than equal to DF. So for that we will find MUW, and let us assume the limiting case of this, that 3/7 XU is equal to DF, and find moment of resistance of web MUW. So again, the formula for this is very simple: 0.36 FCK BW XU into D minus 0.42 XU. This is because of the web, and this is because of the flange. What you have to essentially put the value of XU is 7/3 of DF, right? So when you put the value of XU as 7/3 of DF, and when you substitute all the values, 0.36 FCK BW, 7/3 DF into 500 D minus 0.42 XU plus 0.44 FCK BF minus BW into DF into D minus DF by 2, I get 582.3 kilonewton meter. So essentially what I've got is MUW is greater than MU. If MU is less than MUW, then 3/7 XU is less than DF. How? So we had got MUW greater than MU, therefore 7/3 DF would be greater than XU. So DF would be greater than 3/7 XU, or 3/7 XU is less than DF, or vice versa. So again, this case 2 is wrong for us. So we move to case 3, because obviously if the first two cases are wrong, case 3 is the only correct one, which says that 3/7 XU is less than DF. And in this case we need to find YF. YF is 0.15 XU plus 0.65 DF. So 0.65 into 100, DF value we know. So it's 0.15 XU plus 65. This is what we have simplified for now. And we need to find the actual neutral axis depth XU, and for that we have our moment of resistance formula for case 3, which is 0.36 FCK BW XU into D minus 0.42 XU plus 0.444 FCK BF minus BW into YF into D minus YF by 2. So you have to put this equation of YF here as well as here, and then you will have to solve it for the value of XU. Okay, so it becomes a huge equation, and I'm not sure if you can put this into a calculator and you'll directly get or not. So it's always better to solve it using the normal. You simplify this into a polynomial equation, because you will get an equation of degree 2 and you will get two roots. One of the root would be correct, that would be your XU value, and I get the value of XU is 165.0357. so this is the final value of XU. And after this, after finding the value of XU, we need to find AST, and for that what we have to do, we have to equate compressive force to tension force. So compressive force is 0.36 FCK BW XU plus 0.444 FCK BF minus BW into YF. This is our compressive force. It is equal to 0.87 FI AST. Now YF value, after finding XU, you can find the YF value easily. So it's 0.36 FCK BW XU plus 0.444 FCK BF minus BW into YF is equal to 0.87 FY AST. And when you find AST, you will get it as 2555.8897 mm square. So we got the area of steel required, and now we have to know how many bars we have to provide and which dia of bar we have to provide. So again, we have done this exercise a lot of time. In fact, quite from last 10 to 11 lectures we have been doing the same thing. So I will provide 2 layers of 325 dia bars. You can calculate for yourself and maybe you may get more optimum AST. But what I got, and maybe this may not be the exact optimum AST what is there, but I got 2 layers of 325 dia bars. It means how it will look is, I will have 3 bars, and over, let's say that this is a spacer bar like this. So total 6 bars I will have, because in reality how it is placed is like this same thing, 1 2 3, and in between a very thin rod, a very small rod, and then on top of that the second layer. So this is the spacer bar basically, and here just it is shown a little bit thick. Actually it was not meant for the spacer bar, but okay. Yeah, so now we need to find the minimum and maximum AST, and again we come to this clause of IS 456 which we have used a lot of time for finding minimum and maximum reinforcement. And here you can see that B, what is it, this in this 0.85 BD upon Fy, this AST minimum is 0.85 BD upon Fy. So B, what they are saying is, it is breadth of beam or breadth of web of T-beam. So in case of flanged beams, you will not use the flange width, but you will have to use the web width in this formula. Okay, so it is 0.85 into 250 into 500 upon 500, which gives me 212.5 mm square. So this is the minimum AST, and maximum steel is 4% of BD. So again, B that you have to use here is the web width. Okay, so 4% of 250 into total depth 550 is 5500 mm square, and our AST is lying in between them, so it is okay. And the next steps for this would be the serviceability check, and I will leave that serviceability check on you because we have already done that a lot of time in the previous design numericals. So if you have not seen those previous design numericals of singly and doubly reinforced, kindly check those. You will understand how serviceability check has to be done. So this was it for today's lecture, and we have completed our flanged beam sections. So we have completed the limit state of collapse flexure, and from the next lecture we will be starting with limit state of collapse shear. So till then, take care. Thank you.